Okay, can everybody hear me? Great. So there are a few reasons why you might be tired right now. It's a Friday. It's the last talk of the workshop. It's 4:15. You might be thinking about happy hour in 45 minutes. So I'm going to keep an eye on people. If people look like they're falling asleep, I'll just say happy hour. And then you'll either think this is a happy hour or you'll think about happy hour that's actually happening afterwards. So, all right. So I'm going to be talking about some work we've been doing over the last few years on nonparametric Bayesian time series models, in particular focusing on a model called, which we call the infinite HMM, and then some newer work. And this is actually joint work. The most recent bit of work is joint with Jürgen van Gaal and Yunus Sachi, who are students here, and Yi Tae, who's at UCL. Okay, so here's a sort of broad outline of what I'm going to talk about. The motivation is really to think about time series models, as you know, we're all thinking about here. I'm going to be dealing in discrete time. And when you look at discrete time series models, there are, broadly speaking, two classes of models. There are models that are fully observed. You're trying to predict your observation at time t directly given your observations at previous times, like AR models and things like that, or n-grams and language modeling. And there are models, on the other hand, that have hidden states, things like state space models or hidden Markov models, etc. And I'm generally just a little bit more excited about hidden state models just because you can hope to capture interesting structure in high-dimensional complex time series by invoking the idea that there are hidden states. And hidden state models have been around for a very long time. And one of the most popular kind of hidden state models is the hidden Markov model. These are very widely used. And essentially, the structure of the talk is going to be the following. In blue, I'm going to have a question, and in red is going to be sort of our approach to addressing that question. So first of all, I'm going to talk about one of the problems with hidden Markov models, which is how do you choose the number of hidden states you want to have in your hidden Markov model? And the thing that we've been working on is a nonparametric Bayesian approach to doing this, where you define a hidden Markov model with a countable but infinite number of hidden states. So the number of hidden states is not bounded a priori when you start running your, or when you define the prior on your model. The second question I'm going to get to is sort of addressing a limitation of hidden Markov models, which is in a hidden Markov model, you have a single discrete hidden state variable. And that's supposed to capture everything about the history of the time series that you need to predict the future of that time series. And that seems like a lot of work for a single discrete variable to do. Of course, you know, if you have enough states of that, you can do it. But it seems like we should be able to define more interesting models with many hidden variables at each point in time. And so I'm going to just briefly review some actually kind of now older work we did on factorial hidden Markov models. And then that will lead into the last thing, which is some very, very recent unpublished work that we've done, basically combining the first two things, trying to think about these factorial hidden Markov models and how to make these more flexible, non-parametric, et cetera. So this is what we're going to try to do. Okay. So let's just recap hidden Markov models. One of these buttons is a laser pointer. Oh, tiny, tiny button. Okay. So here's a recap of what a hidden Markov model is. You're trying to model some sequence of observed variables y1 through yt by invoking the idea that there are a sequence of hidden variables s1 through st, and that the hidden variables have a sort of Markov dependency where each hidden variable only depends directly on that same hidden variable at the previous point in time. And then the observed variables are conditionally independent of each other given the hidden trajectory. So the core of a hidden Markov model is this k-state Markov chain. I'm just generally going to use k to denote the number of hidden states in your hidden Markov model. And so the transition matrix in a hidden Markov model is given by a matrix with elements pi ij. It's a k by k matrix, and that just represents the probability that at time t you're going to be in state j, given that at time t minus 1 you're in state I. And I'm, for now, not going to assume that this transition matrix depends on time, so it's stationary. And then that's the core of a hidden Markov model. On the periphery of the hidden Markov model is the observation model or output model. This is what generates the observed data. And we're just going to say that the observation at time t, y of t, is drawn from some distribution f, parameterized by some parameters phi, which depend on what state you're in. So essentially what the state variable is going to do is it's going to pick one of k choices for the parameters that generate your data at that point in time. Okay? So once we've done that, we've defined a hidden Markov model where the parameters of the model are, well, k, the number of hidden states, pi, this transition matrix, and phi, the parameters of the likelihood functions or output models. We're also going to assume some initial hidden state, which we'll take to, not to worry about without loss of generality. We can set it to be in the one state or something like that. Okay, so this is our basic building block. It's been around for 40 years or so, maybe longer now. And if we write down the joint probability of the observed variables and the hidden states, this is joint probability of these two sequences given the parameters of the model. It factors into a product of the probability of each hidden state given the previous hidden state. This is by the Markov property. And then the probability of each observed symbol or observation of whatever kind it is given the hidden state at that point in time. And this transition probability we can write as pi of s of t minus 1 s of t. That's an element of that k by k matrix. And then this is just the emission model for state s of t. So this is just a rewriting of the joint, this should say joint probability of a hidden Markov model. And the picture we should keep in mind is you have some hidden states like these little red dots, and your hidden states jump between some possible values. So here we have just two values that our hidden state can take. And then you have some observed data like these blue things that can live in any kind of space that you want. And essentially we're trying to do several things. We're trying to infer the hidden states from data. And we are also trying to learn what the parameters are from data. So that's a recap of hidden Markov models. OK, so the question is, unless we have some real knowledge about what these states are supposed to represent, if we're going to apply a hidden Markov model to real data, we don't know how to choose k, the number of hidden states. Or rather, I should say, many people have thought about the question of how to choose k. And I'm going to give you a possible solution which I kind of like, and I'll argue why I like it. But I'll acknowledge that there are other ways of approaching this problem clearly. And the solution we're going to propose is the following. We're going to say, if I'm modeling real data, in the real world, it's very hard for me to actually believe that there are some small number k of hidden states actually out there. The real world is just a very complicated place. So rather than pick a k or pick a distribution over finite k's, can I define a model which simply has an unbounded, countable but unbounded number of hidden states it can choose to use, And can I define a model like that in which I can do efficient inference? So essentially what the model is going to be able to do is it's modeling observations. At any point in time, if a new observation comes in and it can't really be well modeled by one of the existing states that it's invoked for modeling the previous observations, then it can say, oh, well, I think I need a new state here. And then it can just grab a new state from its pool of infinitely many states and say, okay, this new state is modeling this new observation. And this is a concept that is kicked around quite a bit in the nonparametric Bayesian community, and I'll try to relate it to things like Dirichlet process mixtures for mixture modeling, et cetera, as well. Okay. So the trick is we want to have an unbounded number of hidden states, but we want to have some sort of reasonable inference algorithm for this. So this is the first part, actually in a lot of ways the main part of the talk, where I'm going to talk about the infinite hidden Markov model. And here is the sort of history of the infinite hidden Markov model. So we can think of hidden Markov models as time-dependent mixtures. And if you have k states, the transition matrix is a k by k matrix. And a sort of graph representing the hidden Markov model is shown by this picture you've seen before. Now, we're going to define priors on the transition matrices of this graph and priors on the emission parameters of the graph in such a way that we can try to take the limit of this model as k goes to infinity. And this is going to define something we're going to call an infinite hidden Markov model. I'm going to define it in a little more detail in a minute. And the idea is that if I were to sample hidden state trajectories from the prior in this model, so this isn't conditioned on data, I'm just sampling hidden states over time. Here are just 4 draws using different hyperparameters of this distribution we're going to define. And what these draws represent are, on this axis we have time. Just focus in on this one first. We have time on this axis, and we have on this axis the identity of the hidden state that's been visited. Okay? So I just ordered them where, without loss of generality, at the first point in time, I'm in the first hidden state. Then I can either stay in that hidden state or visit a new hidden state, et cetera. Okay? And what you can see in all of these pictures is that they're qualitatively different, but what's going on is that as I observe longer and longer sequences, I expect to find myself in new states, and the number of states that I visit is expected to grow with the length of the sequence. Okay? It's a bit like if you're collecting beetles in the Amazon. As you collect more and more beetles, you expect to see more and more species of beetles. Of course, the number of species is bounded, but assume that there are lots and lots of species of beetles, and then you'll just get a growing thing like this. Okay. So we introduced this model in 2002. I think a lot of people ignored it, including us for a while, because basically our inference algorithm for the model was not particularly elegant. Okay. And then in 2005, Tay, Jordan, Beal, and Bly reinterpreted this model within the framework of hierarchical Dirichlet processes. And what they did was they provided a much more efficient Gibbs sampler for our model. And so then I think people started getting more interested in it, so we decided to come back to it. And what we've done recently is try to just simply improve on the Gibbs sampler. And I'm going to argue why Gibbs sampling is actually a really bad idea for time series. And so we're, in our very recent work, we've just been trying to come up with an algorithm where now, finally, we think that we have something we could actually run on fairly big data sets. Okay, so it's not just maybe of academic interest anymore. Okay, and just, I love this picture. I mean, this is the number of hidden states that are visited as a function of time. And one of the things that motivated us is that, in real data, as you observe more and more data, you find more and more new things. So here's a very similar picture. We actually applied this model to modeling the text in Alice in Wonderland. And this MATLAB plot is actually the entire book Alice in Wonderland. Okay? And the way you read the book is, the words go from here to here. That's the end of the book. And if I just were to tell you what these indices here correspond to, which word they correspond to, you could actually go and read the book as you go along here. And what you can see is that Lewis Carroll used more and more new words as later chapters came along. So the number of unique words that are used is actually growing with the book. And this is something that you see in a lot of real data, especially on very large data sets. And that's the kind of thing we want to capture in our infinite hidden Markov model, not in the observation space, but in terms of the hidden state variables that we have. Okay. Okay. So in the 2002 model, what we did was we basically defined a hierarchical urn scheme for generating transitions in the hidden Markov model. And I think this is kind of hopefully an intuitive way of thinking about how the system transitions from state to state under the prior. And then we combine that with the likelihood function, and we do inference. But it's important to understand the prior first. So here is the idea. I'm sitting in some state, I, and I'm going to decide what state to transition to. Okay. And I have the model is defined through 3 hyperparameters, alpha, beta, and gamma. So the first thing we're going to do is decide whether to self-transition from I to state I again. And we were originally treating self-transitions as special things, which I think is sensible. Or to transition to a new state, J, to an existing state, J, so that's this branch, or to consult some other second level process. Okay, and I'll get to that second level process first, next. So the idea is the following. NII and NIJ are simply going to be the number of times I've previously transitioned. Say Nij is the number of times I've previously transitioned from I to J. Okay? So you keep count of the transitions you've done in the past, and then the probability of transitioning from state I to state J is proportional to the number of previous times you have done this already in the past. Okay? So there's a self-reinforcing property to this. If I've gone from I to J a lot in the past, then I'm more likely to go from I to J in the future. And this doesn't come just out of thin air. When we reinterpret the model in terms of a hierarchical Dirichlet process, there's a self-reinforcing property in Dirichlet processes that you get for free, and this is the sort of behavior that you have. So with probability proportional to NII, the number of times I did a self-transition, plus alpha, which is just biasing myself towards self-transitions, I'm going to do a self-transition. And with probability proportional to beta, I'm going to consult something that we're calling the oracle. And then the oracle is going to either make us transition to some state J in proportion to the number of times the oracle chose J in the past. Okay, this is NJO. Or with probability proportional to gamma, the oracle is going to tell us to jump to a brand new state. Okay, so this is how we hop onto a new state. And the stuff on the bottom is just all normalization, so these branches sum to 1. Okay? So with this picture here, you can generate, with different alphas, betas, and gammas, you can generate these sorts of state trajectories if you want. Okay. Okay. So when you look at this, you can see that actually, how often am I going to jump to a new state? Well, that's going to be in proportion to beta times gamma. Okay, so you can get intuitions about what these hyperparameters mean in terms of the growth of new states, the probability of self-transitioning, et cetera. All right. The infinite hidden Markov model is actually closely related to a model which has been very influential in nonparametric Bayesian statistics, which is the Dirichlet process mixture. And let me just try to explain at a very high level why these two things are very closely related to each other. Hidden Markov models can be thought of as time series generalizations of mixture models. Essentially, your hidden state represents what mixture component you're in. You generate from a mixture model. And the only different thing about hidden Markov model is that the mixture component you're in at this point in time depends on what mixture component you were in at the previous point in time. Okay? Now, Dirichlet process mixtures are a way of defining mixture models with countably infinitely many components. So they were introduced, for various reasons, but they're a way of taking the limit of a finite mixture model to have countably infinitely many components. The thing that makes the connection is that infinite hidden Markov models are just hidden Markov models with countably infinitely many states. So in fact, we can derive this infinite hidden Markov model from these Dirichlet process mixtures. And I'll try to explain that a little more. But I hope you get kind of the big picture here. So the first part of that picture is that hidden Markov models are time series generalizations of mixture models. And here's the way to think about it. Consider the probability distribution over y of t, the observation at time t, conditioned on being in state k at time t minus 1. Okay? So this is the probability over y of t given that at time t minus 1 you are in state k. Well, that probability simply sums over the possible states that you could be in at time t, the probability of observing y of t under that state. So this is the sum from 1 to k of the state you could be in at time t, given that you were in at time t, given that you were in k at time t minus 1, times the probability of y of t given that s of t. Okay, and this thing here is the kth row of that k of that big K by big K transition matrix. So that we can write as pi sub k s of t. It's the probability of transitioning from state k to state s of t. And then this is the emission probability distribution over y given by parameters phi of s of t. So that's this expression here. And when you look at this, this is exactly the form that a finite mixture model takes, except that it's a finite mixture model where the mixing proportions are dependent on which state you happen to be in at time k. All right? So that's the link between HMMs and mixture models. Okay. Now, in the infinite HMM, we want to take the limit as the number of states k goes to infinity. And the way this is done in a mixture model is through the Dirichlet process. And the Dirichlet process is something that one can talk about for a long time. I'll give a very brief introduction to a Dirichlet process. So the Dirichlet process specifies a distribution over distributions. And the way we're going to write this is we're going to say G sub k, which is going to be a distribution on some space, the space of phi's parameters of this model, it turns out. G sub k is some distribution. It's drawn from a Dirichlet process where that Dirichlet process has two parameters, alpha, which is called a concentration parameter, and h, which is called a base distribution. Essentially, what these parameters do is that think of a distribution G sub k drawn from the Dirichlet process. The mean distribution that you get, if you averaged many draws of that Dirichlet process, the average thing that you would get would be H. And alpha controls the variance, essentially, around that distribution. Okay. And one of the interesting things about the Dirichlet process is that even if H is some sort of continuous density, G sub k is going to be discrete with probability 1. So in fact, the G sub k's, these distributions, can be represented by a countably infinite mixture of delta functions, where these pi sub k's are going to be the masses of each of the delta functions, and the delta functions are going to occur at locations drawn independently from this base distribution H. Okay. So, so this is just a very, very brief introduction to Dirichlet processes. I'm sure that it's not sufficient if you haven't encountered these before, but I want to just highlight the form of this thing here. It's a countably infinite sum of these delta functions with these weights that sum to 1, basically. And the Dirichlet process here, if you draw a G sub k, this is specifying both infinitely many weights that sum to 1, and it's specifying infinitely many locations of parameters in parameter space, okay, simultaneously. And we're going to use those to represent our infinite hidden Markov model. So here is the idea. At a high level, we're going to take this draw from a Dirichlet process, and we're going to identify the mixture weights in that draw with the transitions of the infinite hidden Markov model. So these pi sub k, k primes are going to correspond to the kth row of that transition matrix in the infinite hidden Markov model. And we're going to identify the locations of the, these delta functions in parameter space with the parameters corresponding to the different states in the infinite hidden Markov model. Okay. So, so this is the high-level description of how possibly one could relate to the Dirichlet process with the infinite hidden Markov model. There is a technicality which I've removed the slides for because it takes a while to explain. For each of the hidden states, we're going to draw a Dirichlet process, draw from the Dirichlet process. So there's a G sub k for each hidden state. But you can't do them all independently because then the locations of the spikes would never line up. So you would actually, it turns out, never visit the same state again. So you need to couple all of the rows of the matrix, all of these draws from the Dirichlet process in order to get it to do something sensible. But I've sort of left out that detail because, yeah. Sorry?
The capital K.
The capital K is for the finite model. This sum goes from 1 to k. So I've written this expression for the finite model, and then we're going to make it have a countably infinite number of hidden states by letting k go to infinity and making these correspondences. Okay. Yeah, they're a bit discordant in this case. Yeah. Okay. So, so in this paper by Tay et al., the paper was focusing, this is a JASA paper that focused on hierarchical Dirichlet processes, and then in a section of the paper they showed how the infinite HMM can be interpreted from that hierarchical Dirichlet process framework, where the word hierarchy comes in here because I said all those draws of the Dirichlet processes for each row of the transition matrix have to be coupled to each other. And the way they're coupled is by having one draw from a Dirichlet process at the top, and then everything is drawn from a base measure, from a DP with that base measure. That's how they're coupled, and that's where the hierarchy comes in. And you can represent this stuff graphically by saying, again, you have the hidden states, the sequence of hidden states, and you have the sequence of observations, and you have a bunch of parameters. For each row of the transition matrix, you have parameters pi sub k, which correspond to that row of the transition matrix. This is an infinitely long vector that sums to 1. And for each state, you also have phi sub k, which are the emission parameters for that state. And this is inside this box here, which represents a plate or replication of these variables from 1 to infinity. So there are just infinitely many of these variables. And this looks nasty because, okay, so we have a statistical model with infinitely many latent variables in here. How are we going to deal with it computationally? And it turns out with some bookkeeping, we only ever have to deal with finitely many of those hidden states. We're just allowing us to pull hidden states out of the pool of infinitely many ones as our computations go along. Okay? So that's the infinite hidden Markov model. And the question is, let's try to do Bayesian inference in this model. How do we do this efficiently? I mean, clearly, exact inference is intractable in any model of this kind. But how do we even define a reasonably efficient MCMC method for this kind of model? So this is what I'll focus on now. And let me just review what's done for ordinary finite state HMMs here in blue, and then what the issue is with the infinite HMM. So in regular HMMs, we tend to think of two different problems. The problem of inferring the hidden states, in other words, computing the probability distribution over the hidden state S of t, given the observations y1 through yt, and all of the parameters lumped together into a parameter vector theta. And this is what's solved usually using the forward-backward algorithm, which is a form of dynamic programming, which is also equivalently a form of the belief propagation algorithm for a graphical model. So these things are all can be all mapped onto each other. Okay? So that's how you infer the hidden states in an HMM. And then the parameter learning problem is usually done in practice using expectation maximization, which is that's the EM algorithm, which was actually first invented in hidden Markov models by Baum and Welch. And so rightfully, it's called the Baum-Welch algorithm for hidden Markov models. Or if you're trying to do Bayesian inference, then you want to not optimize the parameters, but you want to infer the parameters as well as the hidden states. And then the most common thing to do is a form of Gibbs sampling, where you hop back and forth between hidden state sequences and parameters. Okay. Now, in infinite hidden Markov models, in that 2005 paper, Tay et al. Showed a nice Gibbs sampling algorithm that samples from the hidden states and the parameters of the model, jumping back and forth, where for the parameters, you don't actually have to sample from the infinitely many parameters. You only have to sample from the parameters associated with the states that you're currently using to model the data. Because once you've sampled the state sequence, there are only finitely many states you visited for a finite sequence that you're trying to model. Right? But this is unfortunate. This is not very practical because Gibbs sampling can be very slow for time series. Okay? And what we really want to do is use some sort of dynamic programming. So before I go into this, let me just explain why Gibbs sampling is usually a really bad idea for time series. So we have a sequence of hidden states. And the whole idea of a time series model is that the hidden states at one point in time are going to be highly correlated with the hidden states at neighboring points in time. Right? I mean, for most interesting time series, that's the case. Now, if you Gibbs sample at one state variable at a time, what you're sampling is a very highly correlated distribution, the length of your entire sequence. Okay? And essentially, to move around in that distribution, it's going to be incredibly slow. One can quantify these things, actually. But the intuition is that if I want to go, let's say I had two hidden state sequences. And there was a symmetry in my model, and I could go from the all 0 state to the all 1 state and explain the data equally well. Then the time it takes to go from the all 0 state to the all 1 state is going to be incredibly high if you have high correlations between neighboring states. Okay, so just as an intuition, you really want to be able to sample entire state paths, not individual state variables conditioned on its neighbors in time. And this is what we're going to try to do with this sort of dynamic programming trick. So how do we sample from entire state paths in an ordinary HMM? Well, there's a nice algorithm that goes by several names, but I think forward backtrack is one version of the names for this algorithm. And essentially what that algorithm does is it runs the forward algorithm from forward backward in an HMM. That is an algorithm that recursively or sequentially going from time 1 to time t computes the probability distribution over state s of t given all of the observations up to time t. This is like the Kalman filter algorithm, but in discrete state spaces. That's the forward algorithm. And this is an algorithm. It's very straightforward. You've seen these equations before, actually, today. And it's an algorithm that runs in order t, the length of the sequence, k squared, the number of hidden states squared. Okay? And then when you hit time big T, the end of the sequence, what you're going to do is you're going to zip back and generate an entire sample path from the distribution over hidden state sequences. So here's how you do that. At time big T, you have the probability distribution over S of t, S of big T, given all of the observations. And so we can draw a hidden state from that probability distribution. Okay? And now we zip back from time t minus 1 down to time 1, and we draw the previous hidden state now conditioned on the observations up to time t and conditioned on the next hidden state that we've already drawn. Okay, so this will generate a correlated path from the exact posterior distribution over paths in an HMM with given parameters and so on. Okay, so this is much better thing to do than HMMs. This is well known by people who work in this area. Okay. Now we want to apply this idea to the infinite HMM. The problem is k went to infinity, so the algorithm is not practical in the infinite HMM. So we need to finesse that somehow. And so we can't do it naively. A potentially bad idea is let's take these transition matrices. The rows of the transition matrices sum to 1, but they have, they're infinitely long. Maybe we can just truncate we can truncate at some small transition probability. And that's kind of a hack. You can do that, but then the interpretability of the whole thing goes away, and why are you doing nonparametrics anyway if you're going to do that? So that we think is not a very good idea. And it would be only approximately correct. So what we're going to do is we're going to combine a couple of sampling ideas. We're going to combine the idea of slice sampling with this dynamic programming forward backtrack trick that I just showed you. Okay. And this will give us an algorithm that's actually correct in that it has the right equilibrium distribution. So here's the idea. Let's take each row of that transition matrix. This is, for example, the first row of the transition matrix. And we can represent the probability of transitioning from state 1 to state 1 by this height, the probability of transitioning from 1 to 2 by this height, etc. So we have a bunch of sticks that sum to 1 in a particular row of a transition matrix. Now what we're going to do is we're going to introduce an auxiliary variable at each point in time, u of t, which is going to be drawn uniformly from a distribution between 0 and pi sub s of t minus 1 s of t. So this is conditioned on a current path through the hidden states. We're just going to look at the transition probability between s of t minus 1 and s of t, which we've conditioned on. This is just the number between 0 and 1. So this is a uniformly distributed variable between 0 and some number less than 1. Okay? Now, once we've drawn u of t, then this partitions our potential next hidden states into hidden states that have a probability of going to them greater than u of t, and hidden states that have probability less than u of t, like these hidden states. Right? So this is a way of truncating the hidden state space. And obviously, there will only be a finite number of hidden states that have transition probability greater than u of t. Okay? So we have finitely many things greater than u of t, and then infinitely many things less than u of t. Intuitively, what we're doing is an auxiliary variable method in our Markov chain. So here's just 2 time slices of our hidden Markov model. We have the transition matrices here and the emission matrices here. These are the parameters of the model. What we've introduced is a uniformly distributed auxiliary variable that depends on s of t minus 1, s of t, and pi. Okay? But because this variable doesn't affect anything here, it's just sort of an epiphenomenal variable. It's just sitting there. We haven't changed the distribution over any of the stuff in black. Okay? So the auxiliary variable, importantly, does not change the distribution over anything else in the model. And now, essentially, what we're going to do is we're going to alternate between sampling hidden state sequences, parameters, and these auxiliary variables. Okay? And the algorithm is basically going to end up looking like this. So sample the auxiliary variables. Assume you have hidden states and parameters initialized. Sample the auxiliary variables. Then once you've sampled the auxiliary variables, here's the neat thing. The auxiliary variable went from, it was uniform between 0 and this value here, pi of s t minus 1 s of t. Now, if I'm going to sample s t minus 1 and s of t conditioned on u of t, then any hidden state where the transition probability is smaller than u of t is automatically invalid. Okay, so we never have to consider those hidden states. So with a little bit of bookkeeping, we essentially have truncated the possible hidden states we can visit to be finite at every point in time. And this is going to change over time. How many of these finite hidden states we have. And then, so this is, we sample the hidden state sequences in this sort of forward backtrack method. And then we resample the parameters and hyperparameters of our model given the hidden state sequences, et cetera. This is basically a big Gibbs sampler with auxiliary variables. Okay. So the properties this has is that it adaptively truncates the infinitely large transition matrix. We can sample the whole sequence S, and we can do hyperparameter sampling, et cetera. So essentially, we have some experiments where we compare the Gibbs sampler to this, what we're calling the beam sampler, because it sort of keeps a beam of possible options at each point in time. And the experiments are kind of boring. They're basically showing that, the beam sampler is going to be faster to mix than the Gibbs sampler. I mean, there are other statistics we can compute from here. Not dramatically in the cases that we tried, but in some cases it is actually much faster. Okay. We also modeled, for example, characters in Alice in Wonderland, characters meaning like letters in Alice in Wonderland, and we compared them to a different approach, which is based on a variational Bayesian hidden Markov model, where essentially in this other version of the hidden Markov model, you have to try out different numbers of hidden states. And here it seemed to like having 15 or so hidden states, and it produced predictive probabilities around here. In the infinite hidden Markov models, you basically don't have to loop over different size models. You just run it, and it decides how many hidden states it wants. And it generally tends to produce results that are about as good as the best model that tries to loop over different numbers of hidden states. So there's an efficiency to be gained there as well. We looked at some applications of this to change point detection. So here is a one-dimensional time series, which is somewhat heavy-tailed, where it seems to go between different regimes. And the colors here are assignments to hidden states from the infinite hidden Markov model. So, OK, it has infinitely many potential hidden states, but it ends up deciding to use 1, 2, 3, 4, basically 4 hidden states. The point is the pool is not limited a priori, but obviously if 4 seems to be a good number, then it will like to use 4. Okay. And indeed, again, we can confirm that, for example, at a particular point in time, even after the first 5 samples, the beam sampler seems to have found structure in the data, whereas the Gibbs sampler is not finding anything. The Gibbs sampler just takes longer to find structure, and the structure the Gibbs sampler finds is not as good as the structure the beam sampler finds. So I'll skip over that. Okay, so don't worry, part 2 is much shorter than part 1. I know happy hour is starting. Okay, so here's the second thing that was sort of a limitation of hidden Markov models. And that's that idea that I said that the entire history of the sequence is being captured by a single discrete hidden variable. And that just doesn't seem representationally to be a very powerful latent structure to use to capture something complicated. So it seems more natural to allow many hidden state variables, in other words, some sort of distributed representation of the state. So for example, one of the things that motivated us originally is hidden Markov models are used a lot in speech. You could think of the state of a mouth as a person is speaking as being in one of some number of hidden states. But now if you look, if you think about what's happening inside the mouth, you could think about, well, what's the state of the tongue? What's the state of the lips? What's the state of the glottis, et cetera? And you could imagine many, many different state variables corresponding to the different things that are going on in the mouth that are producing the speech utterance. And it would be nice to have hidden Markov-like models, but with many hidden variables. So this motivated this work on factorial hidden Markov models, which is now over 10 years old. So the idea is, in hindsight now, a very simple thing. We just take the hidden state at a point in time, and we now assume that it factors into a bunch of hidden state variables. So at any point in time, we have m hidden state variables. Here it looks like 3. We still have our observations down here. And now, essentially, to make the model somewhat more structured, we're not going to make all of the hidden state variables at the next point in time depend on the entire configuration space of these hidden variables at this point in time, but we can introduce some factorization between the hidden variables. For example, the hidden, at one extreme, the hidden variables might all evolve independently from each other. And this is what's called by the people in the graphical models literature a dynamic Bayesian network. Inference in this can be done with variational methods or sampling, and it's been applied to a number of things. In fact, you saw an application of this sort of model. Chris Williams was talking about condition monitoring yesterday, I think, and it was an application of this class of factorial hidden Markov models, but also for biological sequences and speech and so on. Now, the question is, well, it's a bit annoying to have to choose how many hidden state variables a priori we need to have at any point in time. So can we play the same trick on this model can we now think of the number of hidden state variables as something that we can take the limit of and allow the model to have as many hidden state variables as it wants, essentially. And this is the very recent work that we've just submitted on infinite factorial hidden Markov models, where essentially the idea is each of these chains is a binary chain. In other words, the hidden variables in each chain are on or off, and it represents whether some process has been turned on or turned off. And all these processes evolve independently of each other, and there are as many of these processes as the model wants. In other words, the number is unbounded a priori, and then the observations depend on all of the processes. Okay. So the basic idea behind this, maybe I'll give a different example. I don't know whether this example will work. So this is a probably very boring video of a very toy thing that's going on. So we're generating images, and the way we're generating images is we're turning on and off different visual features, okay, like this horizontal bar or this vertical bar, etc. I'll play it again. Okay. And let me go back. Okay. So essentially, features turn on, sort of like objects appearing. They appear, they stay on for a while, and then they disappear. Okay? This is just a very, very toy thing that's supposed to illustrate the kinds of processes that we might be able to model. Processes in which things appear, stay on for a while, and disappear. And the number of things is something that we don't know a priori. So we're going to assume there can be as many things as we want. Okay? And so, we can define an MCMC sampler for this model, and it turns out that we end up using some of that same truncation trick that I talked about for the infinite HMM, where we introduce auxiliary variables, and that way we truncate the number of chains that we have to consider when we do our sampling here. And I'm not going to belabor this, but we can sample from the hyperparameters and infer the number of hidden states, etc. And how well this mixes is another question. I mean, I think once you start sampling in very complicated models, it's hard to tell how well it mixes. But you can look qualitatively at the results it's producing to see if it's doing anything practically useful. Okay. So here's a more serious application of this. And I'm almost done, basically. The classic problem, a classic problem in signal processing is this blind source separation problem. And the idea is the following. It's like the cocktail party problem in the following sense. You go into a cocktail party, and there are many different people speaking, and you're trying to separate out the different speakers from each other. Okay? So there are two problems here. So essentially, you have a bunch of sources. The sources are the people that might be speaking, the sources of sound, and you have a couple of microphones, which are your ears, and based on the signal on your microphones, you're trying to separate out the sources. This is something that has been solved with the method in signal processing called independent components analysis, and it's been applied to lots of different things, including separating out, for example, brain imaging, different sources of signal in brain imaging data to find different sources of brain activity and things like that. But a lot of those models actually throw away time. So what we want is a model that will be able to do the following. It'll be able to separate out sources. It'll be able to infer how many sources there are. And it will be able to model the fact that when a source is on, it's likely to stay on for a while before it turns off again. Okay? And so this is exactly what we can do with this infinite factorial hidden Markov model. So what we did is we took this is sort of artificial data, but let me explain how we generated it. We took 5 different speakers, okay, meaning people talking, okay. We took audio from 5 people talking, and we mixed them in the following way. We just combined them, assuming there was some number of microphones. We combined them with some linear combination. For each microphone got a different linear combination of the 5 different speakers. And each of the speakers was on or off, meaning speaking or silent, at different points in time. So time is going down this way, and the 5 different speakers are going along this way. Okay? You can also think of it as an orchestra where different players are playing different instruments at different points in time. Okay? But here it was audio from speech. And here are reconstructed hidden variables from the infinite factorial hidden Markov model that I've just described, and from exactly sort of a version of that throws away the Markov dependency of the hidden variables over time. Okay? So we can take that same model and just make time uncorrelated, and so we get this model here. And what you find is that the model that makes use of the time discovers how many speakers there actually are. So this is the number that it actually finds, and it corresponds to the truth here, basically. It fairly reasonably discovers when each speaker is on, and it sort of seems to do a reasonable job if you compare these two. Whereas the model that is still also non-parametric, but doesn't include this temporal dependency, seems to invoke a lot more speakers than actually exist. And the inferences it makes are very choppy in time. It turns on and off way too frequently. Okay. This is when you have more signals than sources. This is slightly harder when you have fewer signals than sources. And again, qualitatively, this is now worse, but it's still much better than this model here. And you can still see the correspondence fairly reasonably. Okay. So I'll wrap up with the following. So the big picture is that a lot of models that people have thought about seem to be very closely related to each other. So we can actually relate models to each other by different operations that we could do, starting from a very simple, humble, finite mixture model. Okay. So here are in color-coded different things you can do to the humble mixture model. Okay. You can consider a non-parametric version which has countably infinitely many components. And when you do that, you get Dirichlet process mixtures that have been very well studied by lots of people. On the other hand, as I described, you can consider a time series version of the finite mixture model, and you get the classical hidden Markov model. And finally, you can also consider a finite mixture model where instead of having one hidden variable corresponding to the mixture component you're in, you have multiple hidden variables. This is sort of a distributed or factorial model, which I didn't really describe. But now you can apply these operations in different ways and get to different models. So from the Dirichlet process mixture, you can consider what would you do if you wanted to model time series with that, and you can get to a infinite hidden Markov model from that. Or from the hidden Markov model, you can say, well, how do I make that non-parametric? And you can also get to this model here. And similarly, from the hidden Markov model, you can say, how do I make it have a factorial or distributed hidden representation? You get to the factorial HMM. And then finally, it seems that you can reach this infinite factorial hidden Markov model through all these different paths by getting a non-parametric version of this, or a time series version of a model I didn't describe, or a factorial version of the infinite hidden Markov model. So I think the nice thing is not to try to sell you on any one of these models, but just to kind of have a picture of how these models relate. And then for different applications, we might want some of these different properties in our models, or we might even want to go in completely other dimensions. And this was kind of shocking to me when I ended up drawing this picture, because I realized I'd been bouncing around this cube for over 10 years and not really knew it. Okay, so the conclusion is HMMs have been widely used. Infinite HMMs provide a non-parametric version that doesn't bound the number of states, but we need efficient inference, and we think this beam sampler might be good enough for reasonable sized applications now. And then we extended this to have multiple hidden state variables in parallel, and there's obviously a lot more to do. We can think of new models. We can think of even faster algorithms for inference in these if we want to apply them to very large data sets. And what I really didn't show you, embarrassingly, is any compelling applications of this stuff. Okay. Thanks.
I mean, an infinite number of binary variable, you can map it one-to-one to an infinite state space.
Yes.
So in which sense is infinite factorial more than infinite?
Yeah, that's a very good question. Yeah. And that's also true for the even for the finite case. If I have m binary variables, that corresponds to 2 to the m states of a regular variable, right? So in what sense is m binary variables more interesting than 2 to the m ordinary variables? And I think there is actually a way to think about this. You can map it to 2 to the m variables, 2 to the m hidden states, but then you lose all the structure that you had in there, okay? In that if I assume that I have m binary processes operating independently, then the transition matrix for that process is completely captured by m 2 by 2 transition matrices. So there are actually very few parameters in that model, even though the model has 2 to the m possible states it can be in. So we have a lot more hidden states, but very few parameters that need to be inferred for what the transition structure of that process is. Whereas if you have 2 to the m states in an ordinary hidden Markov model, you have as many hidden states you can be in, but the transition matrix is 2 to the m by 2 to the m, right? Which is 2 to the 2m parameters. It's a lot of parameters. So sometimes it's just useful to have richer hidden state representations, but smaller parameter spaces. And I think that's the region we're exploring here.
I thought the talk was very interesting. I just have a comment on the computational aspect. I think some credit has to be given to Steve Walker's slice sampling idea, which is very nicely on this problem. I think this is quite related. And actually, Steve's algorithm is based on some of our results on retrospective sampling. And I have a technical report which shows that you can combine these two things to get a much more efficient. So actually, I think there is a way to speed up your algorithm quite significantly by just rearranging the code a little bit.
It might be, yeah. I mean,
there is a way to actually improve on that, and at the same time to make. I mean, my experience is that retrospective sampling is mixing better, but it's much more costly computationally. But there is a way to couple it with slice sampling and speed it up, usually by preserving the good mixing product.
Yeah, certainly.
I think there is a lot of scope in that direction.
Yeah, it would be very interesting to explore. I mean, this is, I think, this is just the first chapter, right? Because really we want to be able to speed all these things up. And certainly I acknowledge that, the slice sampling work is obviously very important in this. Yeah.
Why did you decide to have an infinite number of chains rather than looking at a fixed number of chains with an infinite number of states for each one?
Right, that's a good question. Part of that actually relates to this link here, in that the way, I didn't describe this at all, but the way we started thinking about this model, which I did describe, was because we had worked on something called the Indian buffet process. This is this sort of infinitely many binary hidden variables model. And we wanted to see what a time series generalization of that would look like. And that's what we found here. But there's another reason why I think binary variables are kind of interesting. Because often you're interested in things where either something is on or not. Okay, an object is either there or not. Somebody's either playing their musical instrument or not, etc. And then you can have additional hidden variables for what's going on once that process is present. So in fact, in a lot of these models, and I didn't talk about this at all, we have a binary variable saying on or not, but then we have a bunch of other variables saying what's actually going on once something is on.
Okay.
And so that's how we handle the sort of more interesting complexity that can happen. But the other model that you describe is also something one could try.
Yeah.
And again, in fact, you know,
It occurs in language all the time, and that's where it might be useful. You might be able
it
to
might be
apply it
useful.
to-
And this is where compelling applications are needed, because
Yeah.
you know we can kind of bounce around this cube and other cubes, but really we need to convince people of
Yeah.
how this stuff might be useful.
Yeah, I know you did also some work using a variational approach. Why didn't you present anything?
Yeah, so we haven't developed variational approximations for these models or these models. And
You have a finite version in which you can use a split.
we did a variational version of this model and this model and so on. But you know, and there's a variational version of this model, and you know, it could be done. But I think, or I think it could be done. I mean, it might be really hairy. But my sort of feeling is when we develop new models, because variational approximations introduce another level of approximation, it's often useful first to come up with an MCMC sampler for it. Try it on simple problems where you know you're getting reasonable results. And then once you're really forced to do that very large-scale application where maybe MCMC is too slow, then that motivates you to spend the many days it takes to derive the variational equations. So it's just maybe laziness, but I do think that it's a natural thing to first do the MCMC and then, when you really need it, do the variational approximations.
Any more questions? Okay, let's thank Zoubin once more.